State. I graduated on December 15th, 2012, and right now I am interning at the NASA Ames Research Center before I start my PhD in August. So right now, I left off in San Francisco talking about the fabrication and characterization of nanoporous alumina towards biosensor applications. And I'm going to be talking about that in my poster presentation, so I wanted to focus on my current NASA project, which is the analysis of sugar derivatives and carbonaceous meteorites, and I'm examining them for unusual D enantiomer enrichments, and I'll talk more about enantiomers in a little bit. So, carbonaceous meteorites, they contain a glimpse of early solar system organic chemistry, and what we're looking at specifically are sugar acids. And we're examining them for sugar acids because we believe, sugars are important in life, and that's how we generate energy. So we want to know, well, how did that swap into our human development? So just a little organic chemistry lesson. Chirality. So a molecule is chiral when it has 4 different substituents. So just like your hands are chiral. So if you see the palm as a carbon atom, and then your fingers are on the different substituents. So they're not superimposable mirror images. And they can either be R or S. And R and S basically means that they're different. Well, enantiomers are the same in every physical context, except for the way that they rotate light. So R rotates light in a positive direction, whereas S rotates light in a negative direction. So life is homochiral, which is what we're looking at. So in DNA and RNA, we basically have an L axis. But in space, we found out that we see the D enantiomer, or dextrorotatory, and L is levorotatory. So a way that we analyze our samples, we crush up the meteorite into powder, and then we put it through cation-ion exchange chromatography, which is a purification technique that removes the salts. Quantification and quantification technique. So some data, we are able to see glyceric acid, which is, we see more D than L. So those are the enantiomers. And then we see erythronic and threonic, which are the sugar acids. So in the sugar acids, we see we're getting down in carbon number, which is increasing in how rare it is. So a molecule, it's harder for a molecule to form more carbon bonds because it's a stability issue. So to go down in carbon number, it's getting more rare, and that's how we know that, oh, this hasn't happened on Earth. This is in specific space behavior. And we see ribononic, arabinonic, lixonic, and xylonic. And then what's really interesting and what we want to examine further are the 6 carbons, which is alonic and altronic. And we want to look at the 6 carbon sugar acids because that's really rare on Earth, and that's how we know that there isn't any contamination in our samples, so that we can really get down to the nitty-gritty basics of how the enantiomers switched over from space to Earth. Because in space we have the L and D, and we want to know why does life prefer one enantiomer over the other. And our results indicated that our sugar enantiomers can be separated on our GCMS column, and that the enantiomeric excesses ratios vary. And we are able to see and show that there is an enantiomeric excess. So in conclusion, we saw that the sugar acids can be separated, which is a good thing, and that we can see the enantiomeric excesses, and that the sugar acids can be separated. And we just want to prove that the 6 carbon acids can be separated, and then repeat our experiments. And any questions?
No, unfortunately.